Space can kill you in seconds, not dramatically, not heroically, just instantly. But that's not the worrying part, because some of the things out there don't just kill you, they break the rules of how reality is supposed to work. Objects that can strip atoms apart from a distance, regions of space so empty they distort time itself, and theories that suggest the entire universe could disappear without warning, which is mildly unsettling. These are 7 reasons space should terrify you. Point 1, false vacuum decay. Space isn't actually empty. Even in a perfect vacuum, there are underlying quantum fields, fundamental structures that define how particles exist and interact. And right now, all of physics depends on those fields sitting in a very specific state. The assumption is that state is stable. But according to quantum field theory, there's a possibility it isn't. Instead, the universe could be in what's called a false vacuum, a local minimum of energy, not the absolute lowest possible state. Think of it like a ball resting in a shallow dip on a hillside. It looks stable until it isn't. Somewhere else on that landscape, there may be a deeper valley, a true vacuum. And if the field were to transition into that state, everything governed by it would change. This isn't just theoretical curiosity. Measurements of the Higgs boson, the particle associated with the Higgs field, suggest that our universe might sit uncomfortably close to this kind of metastable condition. Not definitely unstable, but not perfectly safe either. And if a transition were to happen, it wouldn't behave like any explosion you can imagine. It would begin as a tiny bubble, a region where the field has dropped into its true vacuum state. And that bubble would expand at the speed of light, which is a problem because nothing can outrun it. Not information, not warning, not even the knowledge that it's already on its way. As the bubble expands, the fundamental constants of nature inside it would be different. The masses of particles could change. The forces holding atoms together could behave differently, or not exist at all. Chemistry would stop working. Matter would stop holding its structure. Everything inside the bubble wouldn't be destroyed in a dramatic sense. It would simply no longer be compatible with the rules of reality. And because the boundary moves at light speed, you wouldn't see it approaching. There's no flash, no signal, just one moment. And then the laws of physics are no longer the ones you were relying on, which is slightly inconvenient. The reassuring part is that if this kind of decay is possible, it's probably extremely rare, on timescales far beyond the current age of the universe. The less reassuring part is that rare in this context doesn't mean impossible. Point 2, Boltzmann Brains. In physics, entropy tends to increase. Systems move from order to disorder over time, which is why things decay, spread out, and eventually stop being useful. But on extremely long timescales, something strange starts to happen. Given enough time, random fluctuations can briefly create order out of chaos. Not permanently, not intentionally, just by chance. This idea was explored by physicist Ludwig Boltzmann, who suggested that our universe itself could be the result of such a fluctuation. And taken to its logical extreme, it leads to a much more unsettling possibility. Instead of an entire universe forming, the simplest possible observer could form instead, a single self-aware brain, complete with memories, perceptions, and the impression that it has existed for a long time, even if it has only just appeared. This is what's known as a Boltzmann brain, a fully formed consciousness, assembled out of random particles, lasting only for a moment before dissolving back into chaos. And statistically, it's far more likely than the formation of an entire structured universe like ours, which creates a problem. Because if the universe is large enough or exists for long enough, there should be vastly more Boltzmann brains than normal observers like us. Meaning that, from a purely statistical point of view, it would be more likely that you are one of them. A temporary fluctuation with a full set of memories that were never actually experienced. A sense of continuity that doesn't really exist. And a reality that will disappear as quickly as it appeared, which is not ideal. Now, most modern cosmological models try to avoid this conclusion. If a theory predicts a universe dominated by Boltzmann brains, it's usually considered incomplete or wrong, because a universe where random, short-lived observers vastly outnumber stable ones doesn't match what we actually experience. But the fact that this problem even exists means that, at some level, physics allows for the possibility that consciousness doesn't need a history, or a body, or even a universe that makes sense, just the right arrangement of particles, appearing for long enough to think, this all seems normal. Point 3. Magnetars. Most stars are fairly well behaved. They sit there, fuse hydrogen, and mind their own business. Magnetars are not like that. A magnetar is a type of neutron star, the collapsed core of a massive star that's already exploded, which means it's taken something the size of the sun and compressed it into a sphere roughly 20 kilometers across. So far, already concerning. But what makes magnetars special isn't their size, it's their magnetic field. They are the most magnetic objects in the known universe, and not by a small margin. A typical fridge magnet is about 0.01 Tesla. A magnetar, around 10 billion Tesla, which is less of a magnet and more of a fundamental threat to matter. At that strength, magnetic fields don't just affect metal objects. They start affecting atoms themselves. Electron clouds distort. Chemical bonds break down. The structure of matter begins to reconsider its options. If you were somehow within about 1,000 kilometers of a magnetar, which, to be clear, is not recommended, its magnetic field could literally start pulling apart the atoms in your body. Not violently, just very efficiently, and even at a much greater distance, the effects are still impressive. In 2004, a magnetar flare from across the galaxy was strong enough to interfere with Earth's atmosphere from 50,000 light years away, which is the astrophysical equivalent of someone turning on a flashlight and it knocking over furniture on another continent. Magnetars also produce star quakes, fractures in their crust that release enormous bursts of energy. In a fraction of a second, they can emit more energy than the sun produces in hundreds of thousands of years, which feels slightly excessive. The reassuring part is that there aren't many magnetars nearby. The less reassuring part is that nearby, in space terms, covers a very large area. And if one ever decided to express itself in our general direction, there wouldn't be much to discuss afterward. Point 4. The Great Attractor. Our galaxy is moving, not rotating. That's normal. Actually moving through space, along with hundreds of thousands of other galaxies, all drifting in roughly the same direction, which raises a fairly reasonable question. What exactly are we being pulled toward? The answer appears to be something called the Great Attractor, a massive region of gravitational influence, located about 150 to 250 million light years away, in the direction of the Centaurus and Norma galaxy clusters. It's not a single object, more like a concentration of mass large enough to affect the motion of entire galaxy clusters, including our own. And whatever it is, it's pulling us in at around 600 kilometers per second, which is fast enough to be slightly concerning. Now, in theory, this isn't mysterious. Gravity pulls things together. Large masses influence motion. Completely normal behavior for the universe. The problem is, we can't actually see it properly because it sits behind something called the zone of avoidance, a region of the sky obscured by the dense dust and stars of the Milky Way. So we know something is there. We can measure its effects. But observing it directly is inconvenient, which means we're essentially being pulled towards something we can't clearly look at. Always reassuring. Over time, astronomers have identified large structures in that direction, like the Norma cluster and the broader Laniakea supercluster, which likely account for much of this gravitational pull. So it's not a single hidden object waiting for us, more a very large, very dense region of the universe doing what gravity does best, slowly, inevitably, pulling everything closer, including us. Not quickly enough to worry about on a human timescale, of course, but still, it's nice to know that the galaxy has a destination, even if we didn't exactly choose it. Point 5. Cosmic voids. Not every part of the universe is filled with galaxies. In fact, some parts are almost completely empty. These are called cosmic voids. Vast regions of space with very few galaxies, very little matter, and almost nothing happening at all. And when we say vast, we don't mean slightly bigger than usual. Some voids span hundreds of millions of light years, which means you could travel for longer than human civilization has existed and still not reach anything. No stars, no planets, just space. Now, voids form naturally as matter clumps together elsewhere, leaving gaps behind, completely normal. But some of them are unusually empty. One example is the Buddha's void, sometimes called the Great Nothing. It's about 330 million light years across and contains far fewer galaxies than expected. which raises the question, what happened there? Did matter simply never collect, or was it somehow removed? Either way, if you found yourself inside one of these regions, you wouldn't see a sky full of stars. You might see almost nothing at all. No nearby galaxies, no obvious direction, just darkness, stretching in every direction. And because voids expand faster than denser regions, anything inside them becomes increasingly isolated over time, which means if you started there, you might never leave. Not because something is stopping you, but because there's nowhere close enough to reach, which is less dramatic than being torn apart by a magnetar, but arguably worse. Point 6. Gamma-ray bursts. Somewhere in the universe, stars are dying, which in itself is fairly standard, but occasionally, one of them dies in a very specific way and produces something called a gamma-ray burst. For a few seconds, it can release more energy than the sun will produce in its entire lifetime, focused into a narrow beam moving at the speed of light, which is already less than ideal. These bursts are usually caused by either collapsing massive stars or the collision of neutron stars. And when they happen, they don't explode evenly in all directions. They fire out jets, like cosmic searchlights, except instead of light, it's intense gamma radiation. If one of those beams were pointed directly at Earth from within our galaxy, it wouldn't destroy the planet. It would do something arguably more efficient. It would strip away large parts of the ozone layer, expose the surface to lethal ultraviolet radiation, and trigger mass extinction events very quickly. There's even some evidence that events like this may have already happened in Earth's past, which is reassuring, because it means this isn't just theoretical. It's something the universe does occasionally. The good news is that gamma-ray bursts are rare in our immediate cosmic neighborhood. The less good news is that if one did happen nearby and happened to be aimed at us, we wouldn't know until it arrived, which, again, is not ideal. Point 7. The black hole information paradox. Black holes don't just destroy things, they erase information, or at least they appear to. When something falls into a black hole, all of its physical properties, position, structure, state, are lost behind the event horizon. From the outside, it's gone, which would be fine, except for one small problem. In quantum physics, information isn't supposed to be destroyable ever. The laws of quantum mechanics say that information about a system must always be preserved, even if it becomes scrambled or inaccessible. But black holes don't seem to follow that rule. They evaporate over time through something called Hawking radiation. And when they do, there's no clear way for the original information to come back out. It just disappears, which means one of two things has to be true. Either our understanding of black holes is incomplete, or one of the fundamental rules of physics is wrong. Neither option is particularly comforting, because this isn't a small inconsistency. It's a contradiction between two of the most successful theories we have: general relativity and quantum mechanics. Both of them work extremely well until you put them together in the same place, and then they stop agreeing with each other, which suggests that at a fundamental level, we don't actually understand what happens to reality under extreme conditions. Not fully, not consistently. So black holes aren't just dangerous because of what they do to matter. They're dangerous because of what they reveal, that the rules we rely on might not all be compatible, which is slightly concerning. Space isn't just dangerous, it's unpredictable. On scales we don't fully understand, from fields that could collapse reality itself to particles that might rewrite matter, the universe isn't designed to be hostile, it just doesn't care. And most of the time, that's fine, because everything is far enough away, rare enough, stable enough that we get to exist here without thinking about it too much. But every now and then, physics quietly reminds us that this is not a safe environment. It's just a survivable one, which, depending on how you look at it, is slightly less comforting.